Okay, so looking here at problem number 10, be able to describe what these phasors are. Remember that the phasor shows the magnitude and actually the phase of this oscillating function, the sinusoidal function, and the y component of the vector that we'll draw will represent the magnitude of that function. So for example, if I take this point right here, point A, notice that it has a positive value. So it has a positive value here on this axis, and it's also increasing. That's going to put A in the first quadrant because remember these phasors, they go in a counterclockwise direction at a rate omega t, whatever the phase of that function is, and so the y component of this vector gives the magnitude here, and as this vector moves around, it's going to increase its y component. Now if we look at B, it still has a positive magnitude, but it's decreasing. That's going to put B in the second quadrant, because as this vector moves in this direction, the y component of it will decrease just as it does here. Now C has a negative y component at its maximum. That means that C is going to be right here. It is on the y-axis, on the negative y-axis. Negative because this is in the negative part of the function. And then D over here, I have the y component is positive, so it's going to be in this direction. So this is D. One I didn't ask, but I could have. Let me just go ahead and point it out here. What about, say, right here? This is going to be either on this axis or this axis, and notice that it is now increasing as I move in this direction, so that's going to put it on this axis, because as this moves in this direction, the y component will increase and become positive, just as this function does. So if I call this E, E would be on the positive x-axis, the phasor. So be able to interpret these phasors. They're a really useful tool when you're combining, when you're trying to analyze, for example, an RLC circuit, as we've been doing, these oscillatory functions. And it could be something that you see again. You won't see it in PChem, but some of your engineering students might see phasors again, and hopefully you'll remember some of this. Let's look at this transformer. I have this transformer. It tells me that the primary voltage is 100 volts and that there are 4 turns of wire over here. And I want to know what is this voltage. And this is, there are 8 turns of wire here, all around this iron core, which is, it's a laminated iron core, so that the electricity doesn't actually flow through the core, but you get this changing magnetic flux in the core due to the wires. Now, each turn of wire has the same EMF. Each turn here and each turn here, because they're both experiencing the same change in magnetic flux, so each turn of wire experiences the same EMF. So if this is my primary voltage, I'll call this VP, and over here this is going to be my secondary voltage. I can describe the EMF of a single turn of wire as either VP over NP, that's the number of coils, this is NP right here, the number of turns of wire, or the turn of wire can also be VS over NS, where this is NS. So I get VP over NP equals VS over NS, and here I'm looking for the secondary voltage, so I'm going to say VS is equal to VP over NP, or VP times NS over NP. So that's going to be VP, which is 100 volts. And now the question of is it a step up or a step down transformer is dependent upon the value of this ratio. And NS over NP is 8 over 4, which is 2. That makes this 200 volts. So that's my answer. That is my secondary voltage. And the second answer of this is a step up transformer. So if NS is bigger than NP, then it's a step-up transformer, and if it's the opposite, it's a step-down transformer. That is, if I had more coils over here, then I would have actually a drop in voltage. So if it was switched the other way around, it would be 100 volts and 50 volts. And let's see here. We'll do this last question. RLC circuit has a resistor of 100 ohms. Actually, I'm going to hold off and do this in just a little bit.